Welcome to Elementary Real Analysis. Today we are going to explore one of the most beautiful and foundational ideas in mathematics, the Bolzano-Weierstrass Theorem. Imagine a chaotic system that seems to wander endlessly. What if I told you that within that chaos there is always a hidden, predictable order? Let us dive in and discover why. Now that we understand what our topic is, let us look at the basic building blocks. Why do these definitions matter? Because before we can find order, we must define our constraints. Think of an infinite number of pigeons in a small, fenced in backyard. Because the yard is bounded, the pigeons cannot spread out forever. Eventually, they must crowd together. In math, a sequence is our endless list of pigeons. Bounded means they are trapped in the yard. A subsequence is just us focusing on a specific group of them. And convergent means they are crowding around one exact spot. These definitions lead us directly to the heart of the matter. The Bolzano-Weierstrass theorem formally states that every bounded sequence of real numbers has a convergent subsequence. But what does this actually mean for us? It means that if you have an infinite list of numbers trapped between two solid walls, you can always cherry pick a smaller infinite list out of it that heads straight toward a single exact destination. Even if the original list jumps around wildly and never settles down, there is always a hidden pattern inside it that does settle down. It is a mathematical guarantee of order. Before we move on to the proof, let us see this with a concrete example. Here is the formula for a simple alternating sequence. Conceptually, this formula creates a list of numbers by raising -1 to increasing powers. Let us break down the symbols. The variable x sub n represents the actual number in our list at a specific position. The letter n is our position index, which counts upwards like 1, 2, 3, and so on. As the index n increases, the power changes from odd to even, which physically causes the output to flip back and forth between negative and positive values. Now that we have our formula, let us evaluate it step by step. We are given the alternating sequence and we need to see if it contains a convergent subsequence. First, we plug in the first few values of n. We get -1, +1, -1, and so on. Because it just bounces back and forth forever, the main sequence clearly does not converge. However, we must check if it is bounded. By taking the absolute value, we see that every term is less than or equal to 1. It is completely trapped between -1 and +1. Since we established the sequence is bounded, we can now extract our hidden pattern. We choose to pick only the even index terms from the original list. We introduce a new counting index, k, and multiply it by 2 to perfectly target the second, fourth, and sixth positions. When we plug this even power into our formula, -1 raised to an even power is always +1. Our new subsequence is just an endless list of positive ones. Physically, this means our extracted pattern has instantly settled on a single destination. The limit is exactly 1, fulfilling the theorem's promise. Now that we have seen a basic example, let us look at a slightly more complex formula using a trigonometric function. Conceptually, this formula uses the sine wave to generate our list of numbers. Let us look at the symbols. The variable y sub n is the value of our sequence. The sine function takes an angle and outputs a wave pattern. The letter n is our position index. As n increases, the angle grows, which physically moves us along the sine wave, causing the output to rise and fall smoothly between its natural maximum and minimum limits. Let us apply this trigonometric formula to see what kind of sequence it produces. We are given the sine sequence and asked to find a convergent subsequence. We start by plugging in the first few values for n. This gives us +1, 0, -1, and 0. This exact four-step pattern repeats endlessly. Because the numbers keep moving around, the overall sequence does not converge. But why did we choose sine? Because the sine function is naturally restricted. It can never produce a value larger than 1 or smaller than -1, meaning our sequence is perfectly bounded. Knowing our sequence is bounded, we can now hunt for a stable pattern. We decide to extract a specific subsequence by taking every fourth term from the original list. We use the index 4k to skip the messy alternating terms and focus on one specific part of the wave. When we simplify the math, we are evaluating the sine function at multiples of 2 pi. The result of this is always exactly 0. Physically, this means we have isolated the exact moments the wave crosses the horizontal axis. Our subsequence is an endless list of zeros converging perfectly to 0. Before we prove why this always works, let us look at a visual representation of what we just did. On the screen, you are seeing a graph with the position index on the horizontal axis and the sequence value on the vertical axis. Notice the solid black lines at the top and bottom. These are our strict boundaries at positive and -1. The gray zigzag line is our original chaotic sequence, bouncing around unpredictably. But look at the thick red line. By carefully selecting specific points, we have extracted a subsequence that smoothly flattens out, converging perfectly to a stable limit. This diagram shows exactly what the theorem guarantees. Now that we have seen this visually, let us understand how to prove it mathematically. We will use a beautiful concept called the peak point method. Why do we need this? Because to prove the theorem for every possible sequence, we need a universal way to find order. Imagine standing on a mountain range where every peak is a number in our sequence. A peak point is a special spot where, if you look forward, you only see downhill or flat terrain. Nothing ahead of you is ever taller. By hunting for these peaks, we can force any chaotic sequence to reveal a hidden one-directional path. Let us look at the mathematical definition of this peak point. Conceptually, this formula simply states that our chosen point is the highest remaining value in the entire infinite list. Let us define the symbols. The variable x sub m represents the value of our sequence at a specific position m. The variable x sub n represents any term that comes after it. The hidden condition here is that the index n is strictly greater than m. If this variable x sub m is greater than or equal to every single x sub n that follows it, it is officially a peak point. With our peak point defined, we can begin the proof. We are setting out to show that every sequence has a one-directional path. We split this into two logical possibilities. Let us assume case 1. Our sequence has an infinite number of these peak points. If we simply walk from peak to peak, collecting them in the order they appear, what happens? Because every peak point is, by definition, taller than everything after it, the next peak must be lower than or equal to the current one. Mathematically, this creates a chain of decreasing values. We have successfully extracted a decreasing subsequence from our original chaotic list. This sets us up perfectly for the next step. But what if the sequence does not have infinite peaks? This brings us to case 2, where the sequence has only a finite number of peak points. In this scenario, we simply walk past the very last peak. Once we are past it, no term is ever taller than everything after it. Mathematically, this means that for any number we pick, there is always a strictly larger number somewhere further down the line. By repeatedly hunting down these larger numbers, we create a chain of increasing values. We have successfully extracted an increasing subsequence. So, whether we have infinite peaks or finite peaks, we always find a one-directional or monotone subsequence. We have established that every sequence contains a one-directional subsequence. Now we bring in our boundaries to finish the proof. We know our original sequence was trapped between -m and +m. Because our extracted subsequence is just a part of the original list, it is trapped by these exact same walls. It is impossible for it to escape. We now have a subsequence that moves steadily in one direction but cannot go past a solid wall. By the monotone convergence theorem, a sequence that only goes up or down but is blocked must eventually crash into a limit. This gives us our final result. The subsequence converges to a target number L, proving the theorem. We have covered the full journey of the Bolzano-Weierstrass theorem. Let us reinforce the most important ideas. First, infinite chaos within a confined space must always contain a hidden order. If a sequence is bounded, you can always extract a subsequence that converges to a specific limit. Second, this is not just an abstract trick, it is a mathematical safety net. It bridges the gap between wandering sequences and predictable limits. Finally, this theorem is the backbone of advanced calculus and physics, ensuring that optimization problems in closed systems actually have solvable answers. You now have the tools to find stability in seemingly unpredictable systems.